Bismillah ar-Rahman ar-Rahim. Welcome to this lecture on optimization techniques. Today we will talk about some iterative algorithms for optimization. So this is the subject. Iterative algorithms for optimization. What do we mean by iterative algorithms? It means that you start from an initial point and you move by iteration gradually towards the optimum value. So the objective here is to develop algorithms to optimize performance index. F of x. Okay. Next. Optimize here means to find a value of x that minimizes f of x. So we're trying to optimize here to minimize. Maximize, we discussed it before. You can multiply the function by negative sign and then you minimize the negative, which is the maximization. So you can do that. Okay. The algorithms here we will discuss are iterative ones. What do we mean by iterative ones? We begin with some initial guess x0 and then update our guess in stages according to an equation of the form x at k plus 1 iteration equals to x at the kth iteration plus alpha sub k times p sub k, or delta x sub k, which is equal to x sub k plus 1 minus x sub k equals to alpha sub k p sub k, where the vector P sub k represents search direction, and the positive scalar alpha sub k is the learning rate. Okay, which determines the length of the step. So the equation here, either here or there, it's the same equation. It means that in the next iteration, if this one you go in a direction such that x of k minus k, this one will give me f of x that is less than the one previous to it, okay? So this is what we are looking for. So, choosing the vector which represents the search direction, it states the form of the type of the iterative algorithm that we are using. So we will first discuss something called the steepest descent method. Steepest descent. So the steepest means the going down, at most going down, and ascent is up, descent is down. So we are going downhill with the function and going towards the minimum. In every step we are going downhill the function. Okay, so we would like to have the function decrease at each iteration. So I'm looking for f of x, trying to minimize it. So if I'm taking x here to be x of k, the next one, x of k plus 1, should have f that is less than f at xk. Okay, so in other words, we should have f of x at k plus 1 definitely less than f at x at k. This is what we are looking for in each iteration, until we reach some criterion to stop our algorithm. Okay. So consider the first order Taylor series expansion of f of x about the old guess, which is x at k. So the expansion at the new guess should equal to f of x k plus delta of xk. So this is equals to f at xk plus gk transpose delta of xk. gk is the gradient of f evaluated at the old point, which is xk. So where gk is the gradient vector evaluated at the old guess تخمين السابق xk. So gk is equal to the gradient of f at xk. Okay, for f of xk plus 1 to be less than f at xk, the second term on the right hand side that is this one here. This is what I'm talking about. The second term on the right hand side must be negative. So this one must be negative, so that this one to be less than this one. So this one should be negative, subtracted from this one. So f of x k plus 1 should be less than f of x of k. Which means that gk transpose delta x at k equals to gk transpose delta xk. I'm going to take delta xk here and substitute it with this one. So this is equals to alpha k gk transpose pk less than 0. Okay. From where we got this? We got this here, delta, from this one. Here represents search direction. So what is the best search vector P, the best P vector that will give us the steepest descent method? So if we say, so usually alpha k is positive small number. So it's positive, sorry. Positive small number, which means that still gk transpose times pk less than 0. So any vector pk that satisfies this equation is called descent. So the descent direction, it's going towards the negative or towards the minimum. any vectors. This is an inner product between two vectors. G is the gradient, P is a search vector. Choosing this one to be in a way such that the whole thing is negative, then this is called the descent direction, going in the negative of the gradient, negative of the gradient. Now, to get the steepest direction, we say that pk should be with the negative of gk. So, what is the direction of steepest descent? This will occur when GK transpose PK, the inner product, which is the magnitude of this one times the magnitude of this one times cosine theta, give me the maximum negative. Maximum negative when both are in opposite direction, 180 degrees between themselves, is most negative. So this is the inner product of the gradient vector and the direction or the search direction that we are looking for. So this will be most negative when the search direction is chosen such that to be in the opposite direction of the gradient. So the negative of the gradient, I'm going to put it as I put the symbols. So the search direction will have 180 degrees between it and a gradient, so that this one will be most negative. -1 is the cosine of 180 degrees. Hence, so this is what we call the steepest descent. Descent means they are going with every step you are going downhill. Now, if you are going downhill with the maximum, so you have the steepest descent. This happened when your vector or search vector is with the negative of the gradient. So using this information, produces the method of steepest descent, which says that xk plus 1 should equal to x at k minus alpha k times gk. Where, as we mentioned, gk is equal to the gradient of f at xk. Okay. One point here, one important point here is how to choosing the learning rate, alpha sub k. Okay, so this is some important issue. So let's just take a while here. And steepest descent means that you are going step by step iteration first iteration initial guess, you find the gradient, you multiply it by step size. With a negative sign, you find x of k plus 1. You plug it in through f of x and you find that f of x is reducing every time you are going downhill until you reach the minimum point. Okay, now alpha k is the step size. A step size is a very important issue. Sometimes if you have a very large step size, then you are oscillating around the minimum. If you have a very small step size, then you are moving with a very small steps, which will take very long to reach the very long iterations, number of iterations to reach your minimum. So this one has to be picked in a clever way. There are two methods to find, or we will suggest two methods. Maybe there are more than that, but we will suggest two methods to choose the learning rate in this subject here. So method one says that choose alpha k to be a fixed value. For example, alpha k equals 0.02, or use variable but predetermined values. For example, alpha k equals 1 over k. So it will reduce alpha k as you go further in iteration. The step size will be reduced further and further. It will be smaller and smaller. With large iterations, this one will be very large, or large, relatively large. If you go for beyond 100, then you have 0.01. If it's k equals 1000, then this one is 10 to the minus 3 step size. Okay, the other method is to do some optimization for alpha k. So we will optimize alpha k. So method 2. We will minimize f of x with respect to alpha k at each iteration. In this case, we are minimizing along the line xk minus alpha k gk. In other words, choose alpha k to minimize f of xk plus alpha k pk. Okay, so we'll take this for quadratic functions. So we are using quadratic function, which is most of the time the case, because most of the time when you minimize this one is the sum of squares of errors, so it's a quadratic function in most of the time. So in quadratic functions, it is possible to perform the linear minimization analytically. So we can do it analytically. We can find the derivative of the line or of the function, the minimization, taking the derivative of this function with respect to alpha. Okay. So the derivative of f of x k plus alpha k pk with respect to alpha k can be done as follows. The Taylor series expansion of a quadratic function f of xk plus alpha k pk is f of xk plus alpha k pk equals to f of xk plus alpha k, the gradient transpose of f of xk times pk plus 1/2 alpha k squared pk transpose Hessian of f of xk times pk plus 0 terms because you have a quadratic function. So the quadratic functions only have an expansion up to the Hessian. The upper terms are 0, and this is an exact. It's not an approximation. Okay, now if I'm gonna do d by d alpha of f of x k plus alpha k pk, the first term will be 0, the second term will be the gradient transpose f of xk, so this one is constant with respect to alpha, times pk plus 2 times alpha, so you have alpha k pk transpose Hessian squared f of xk pk, and this is equals to 0. So you have this one plus this one equals to 0, or alpha k equals to minus the gradient f of xk times pk over pk transpose Hessian squared f of xk pk. And we say that this is equals minus gk transpose pk over pk transpose AK times PK. Okay. So, where A is the Hessian evaluated at xk. So, A where AK is the Hessian matrix evaluated at the old guess. The old guess xk. So AK equals to the Hessian. Okay. The search direction so the search direction for steepest descent is the negative of the gradient, i.e. PK is equal to minus GK. Okay. Let's try to do this through an example. We have f of x equals to 1/2 x transpose times 2, 1, 1, 2 times x. This is a second order quadratic equation. If you expand it, it's 1/2 times x1, x2 times 2, 1, 1, 2 times x1 and x2. So you have two variables. If you expand this, multiply this, so you can have 1/2 times 2x1 plus x2, and the other term is x1 plus 2x2 times x1, x2. Okay, so f of x equals to 1/2 2x1 squared plus x1, x2 plus x2, x1 plus x2, 2x2 squared, which is equal to x1 squared plus x1, x2 plus x2 squared. So this is our f of x1 and x2. We need use steepest descent method with alpha k chosen by method 2 to find the minimum. Okay, use the initial guess x0 equals to 0.8 and minus 0.25. So this is an example. We have f of x in this way. Actually, you have, this is your function. We put it in this form because we know that this is a, which is equal to the Hessian. So this a is the Hessian actually. Okay, so f1 of x1 and x2 is equal to this one. We need to use the steepest descent with alpha k by optimizing through the line. Alpha k is chosen by method 2 to find the minimum, and we use the initial guess in this manner. Okay, so the first thing to do is we will find the equation for the gradient. The gradient g which is equal to the gradient of x1 and x2, and this is equals to 2x1 plus x2, and this one is x1 plus 2x2. So this is the gradient. The Hessian two, 1, 1, 2. So we will find the first direction is equal to minus g0. The direction is in the steepest descent, it's the negative of the gradient, and this is equals to minus the gradient of f at x0, which is equal to 2 times 0.8 minus 0.25, and with a minus sign outside, and 0.8 plus 2 times minus 0.25. So our P0 is equals to minus 1.35 minus 0.3. So alpha 0 is equal to minus 1.35.3 times minus 1.35 minus 0.3 divided by minus 1.35 minus 0.3 times 2112 times minus 1.35 is 0.3. And this is equals to 0.413. So this is alpha 0. You multiply it to find the value of x1. So the value of x1 is equal to x0 minus alpha 0 g0, or plus alpha 0 p0, it's the same. So this is equals to 0.8 minus 0.25 minus 0.413 times the gradient at 0, which is 1.35.3, and this is equals to 0.24 minus 0.37. So you have x1. Now x1, you will take it, find the gradient at x1. The Hessian is constant. Find the gradient at this point here. So it's 2 times, instead of 0.8, 0.24 minus 0.35, and the other one is 0.24 plus 2 with a negative sign. Find P0, apply it to find alpha 1, find the next iteration, and please, as practice, do the next 5 iterations. Okay, the next 5 iterations, and find x5. Okay, this is also part, this is part of your homework on next Thursday. Okay, I will just stop here, look at this, try to grasp the concept, and we will continue further next time with the Newton's method. Thank you very much for listening, and I hope that you will find this lecture very interesting. Bye-bye.